Let's begin. Thank you for coming. It's my pleasure to introduce Professor Geordie Williamson from University of Sydney. His title is, Can we describe canonical bases as the solutions of optimization problems?
Thank you, Hyun. And yeah, so thank you very much to Hyun and Hyun for the hospitality. Thanks for having us. Yeah, so maybe the first time I came to Korea was, I think, maybe in 2017 or 2018. And I first went to Daejeon and gave some talks in KAIST, and it was very nice. And then I came back and gave one talk in Kias. And I remember after the talk, Junwook, who was my host at the time, said, "This was a very nice talk, but I have absolutely no idea why you care about this problem." And I really appreciated the honesty, so I will try to explain a little why I care. So yeah, and the other thing that I want to just emphasize is that I know some of you, but a lot of you I don't know what you're interested in, and so please ask a question, and I'm not attached to finishing this talk or going in any particular direction. Okay. So two goals. So the first one is, so there's these things called canonical bases, which are, I would say, central in modern representation theory, modern geometric representation theory in particular. And I will explain a little bit the classical way in which one thinks about canonical bases in a second. But I think that it's possible that there's just completely different ways of thinking about canonical bases, which we haven't yet discovered, which I think would be very interesting. So the first goal is find new ways of thinking about canonical bases. And the other goal is to advertise canonical bases as an interesting source of problems for reinforcement learning. RL, so this is a part of machine learning in which so in some sense so reinforcement learning is the type of thing that, the type of algorithm that people use, for example, when you have a computer playing Go. So the idea is that you're in some environment and you take various actions, and then these actions may have negative consequences, but those negative consequences will only be clear much later, for example. So this is a typical example of reinforcement learning. So so another way of saying it is you have some kind of reward and you would like to maximize that reward long term. And I think this is very interesting. And in some sense, like, I haven't yet reached this part of the project. So this paper, so I essentially all the statements that I'll make that are theorems or computations in this talk are in this paper on the archive. But in some sense, like, this paper is meant as a kind of baseline for this stuff. So this paper is kind of what you can do using classical optimization techniques. And then the idea is now to contrast this with what you can do with reinforcement learning. Yeah. So one way of also thinking about reinforcement learning is sometimes it's a way of producing optima to certain optimization problems, which are just way beyond kind of standard optimization techniques. Okay. So the idea of canonical bases. I would say the idea is that kind of basic objects in representation theory. So examples might be the group algebra of the symmetric group. Or the enveloping algebra of a complex. Or, so this is a highest weight module. So these are, in some sense, like the bread and butter of representation theory. So these objects admit very interesting and non-trivial bases. And typically, these are only visible after introducing quantum parameters. So they're typically only visible after quantizing. Introducing Q or some other parameter. So kind of very strange story. So you start off with something like the group algebra, the symmetric group. And this is deformed into something called the Hecker algebra. And then somehow, so this is over. So yeah, so I'll explain this story in detail in a second. But this is an algebra over kind of initially people viewed it as an algebra over Q, but then for whatever reason, we now call it V, but it's just another parameter. And then here you can define some basis which depends in an essential way on this deformation. So you define the cardinalistic basis. Basis Vx. And now you can kind of specialize V equals 1 if you want. And you get some interesting basis for CSN, but there is no definition of this basis if you're not allowed to perform this deformation. Absolutely, which is kind of an interesting situation. And also, from the very beginning, when this basis was introduced, there's kind of a problem. Like, can we, so this basis, if you write it in terms of the standard basis of the symmetric group, so you get a whole bunch of numbers, and these numbers are really central to representation theory, and yet these numbers have no definition using only this. Another example is you might take UG, and this admits a deformation to UQ of G, quantum group. And then this gives rise to the canonical basis. And again, you can specialize. And get a basis for U of G. And exactly the same thing happens for V lambda. So V lambda becomes can be quantized in an essentially unique way to a module over the quantum group, and then you get an extremely interesting representation, an extremely interesting basis of this module, which again has no, in certain cases, it has a very clear definition in the non-quantized setting, but in general there is no definition. Yeah, so this kind of, so maybe just to provide some kind of sense of the kind of amazingness of this, we know that any representation of SL2, any finite dimensional representation of SL2, all its weight spaces are one-dimensional. And so if we fix a highest weight vector, then there's some easy recipe for producing a canonical basis of the whole module. And this fact for SL2 allows you to do many, many things. Very beautiful, simple thing. Yeah? And now you can ask yourself, I think it's an incredibly natural question. Okay, so, imagine that I have SL3. So this is generated as a Lie algebra by E alpha, F alpha, and E beta, and F beta, two simple roots. So now it's very natural to ask, if I've given a highest weight representation of SL3, can I find a basis for any highest weight module such that when I restrict it to these E alphas and F alphas and E betas and F betas, I just get these SL2 strings? That's I think, incredibly natural question. And then you try to do it, and it just never works. You just can't do it. And then the point of the canonical basis is you can do it if you so such a basis exists if you allow error terms involving Q and higher powers of Q. Okay, and this is the Kashiwara's crystal. So if I give you a simple highest weight representation of SL3, then once I quantize, once I have this Q, it has this beautiful basis where these E alphas and F alphas are just these SL2 strings going all over my module. But I have to have these error terms which are encapsulated by a Q. And and once I fix this structure, it's very, very rigid structure on my module, but you can kind of tell that, like, once you specialize that Q to 1, you can't tell what the error terms are.
What's the interpretation of the error terms? Is there one?
I mean, in some sense, so there's this beautiful start of this paper where, if you're interested in it, it's called On Crystal Bases by Kashiwara. And then he says, quantum groups come from statistical mechanics, where Q is essentially temperature. Okay, in Kelvin, So absolute temperature. And then so Kashiwara says, okay, if this is temperature, something remarkable should happen if I freeze my module, if I send my Q to be 0 Kelvin. Yeah? And when the module freezes, you get this incredibly rich combinatorial structure. But then when you heat up your module, you know, you have these error terms that come in from these Qs. Yeah? And I think that one sentence in Kashiwara just gives so much intuition for what happens in this story. Okay, so it's super important. So I don't want to like. So I'm gonna for the rest of the talk, I'm going to focus on. So this will be focused. But we've done quite a few experiments for the quantum group and for its highest weight modules, and a similar story seems to be true. Okay? So for lack of time, I'm not going to talk about this, but one should imagine that a very similar story holds there. Okay? Yeah?
So you consider the whole quantum group or half of quantum group there? So when you consider the Lustig's basis or Kashiwara's basis, that's usually the half of quantum group.
Yeah, absolutely. So yeah, so typically, I mean, what you're referring to, so typically you'll take UQ or something like n minus. So this is generated by lowering operators. And this is the first place where the canonical basis lives. Okay. And this canonical basis has another absolutely amazing property, which I think if you saw it, you'd just be like, oh my, like this is clearly like such an amazing thing. So there's this basis of this called the canonical basis. Now, if you take any highest weight module and fix a highest weight vector, then you can act by these lowering operators on that highest weight vector. And this basis has the remarkable property that such action is either 0 or a basis. Okay. So this is a kind of universal canonical basis for any highest weight module in this negative part. Yeah. But now you can also pass to Lustig's dot form of this, and then form a canonical basis of the whole dot form. So yeah, I don't want to give too much detail and exact. Like when we've done experiments, we've always considered the canonical basis in a given highest weight module. But thanks for the question. Yeah. Thank you. Are there any other questions at this stage? Okay, so now I'm going to focus on this a little bit. So maybe just one more remark, which I'll just make verbally. So maybe, so the written remark is, they're very subtle. And I'll just give a couple of examples of this phenomenon, okay? So in the 70s, there was another basis of this group algebra constructed via something called the Steinberg variety. So there's some algebraic variety whose Borel-Moore homology becomes isomorphic to the group algebra. And you get a natural basis inside this algebra by taking fundamental classes of irreducible components. This basis yields a basis which looks enormously like the specialization at V equals 1 of the Cauchy-Lipschitz basis. So this was checked in the 70s for like up to n equals 6 or something, and you always get the same basis. And then Cauchy and Lustig conjectured a geometric property, which is called irreducibility of characteristic cycles, which would have implied that this basis is always the canonical basis. So that would have given a geometric incarnation of this specialization. Yeah? And this was widely believed to be true. Like if you read papers in the 80s, they just think it's true. And then 1998, there's this famous paper of Kashiwara and Saito where they say it's wrong. And it's wrong in some very, very difficult to find example. So there's 8 factorial is something like 40,000 something. I don't know, probably someone knows. And there are 38, so there's 38 elements for which this is different. And it's different in a very, very tiny way. So it's like, yeah. So the canonical basis is like something like blah plus blah. And then the characteristic cycle basis is just blah. Yeah. So that's the first example. And then there's also examples in canonical bases where people, like Lustig has this dual semi-canonical basis. And then there's many examples where this agrees with dual canonical basis. And there's also this famous Bernstein, cluster algebra group, Zelevinsky, Bernstein-Zelevinsky, I think. They have this conjecture that the dual semi-canonical basis of the quantum group has some multiplicative property, which it has in many, many small examples, and then Leclerc finds a counterexample in the 2000s. And so there's a lot of, this theory is kind of, has many examples of overwhelming computational evidence for something to be true, and then it just being slightly wrong. And then in massive examples, you expect it's just wrong all the time, inconsistently. Yep. Okay, so things are up. Which also makes it kind of fascinating and cool, I think. So Hecker algebra. So I'll just concentrate on W equals Sn, so the symmetric group. And then we'll denote S to be the simple transpositions. W, simple transpositions. And then we have the length function. Which is how many simple transpositions you need to write an element. And Bruhat order. Okay, and I'm hoping you know what these things are. Tell me if you don't. But it probably shouldn't be too critical. So we take Hn is a free so I take a free module over ZBB inverse. And it's a theorem that there exists a multiplication on this. There exists a unique multiplication such that delta x delta s equals delta xs, the length of xs. And here x is in W, S is in S. So my claim is that there's a multiplication on this free module that satisfies these rules, and that very easy to see this uniquely determines the multiplication, and the existence is a little bit more tricky. And then each so if you expand out, so each delta x is invertible, which is another thing that one can check. And one defines H goes to H bar via and this is the so-called doesn't matter so much. So I'm saying there's an algebra. And so the important thing to notice is that if V is 1, then this term disappears, and I just get the multiplication in the group algebra. So this is a deformation of the group algebra of the symmetric group. So you can kind of imagine that, like when you multiply two elements inside this algebra, you get basically what you would expect from the symmetric group plus a whole lot of error terms involving like V inverse minus V. And then theorem. So this was the kind of first instance of a canonical basis. There exists a unique basis Bx such that there's two conditions. So the first one I want to denote by B triangle, so Bruhat upper triangular, which is the statement that Bx is equal to delta x plus lower terms, where these hy that's the first condition. So this says this basis, if I imagine my Bruhat order is kind of, so at the bottom I have identity, the top I have the longest element, then I have all my elements down. So this is saying that this is the characteristic basis that I'm defining here. It will have leading term delta x, and then it'll have a whole lot of complicated stuff below. Okay. And in self-duality, which is that Bx bar equals Bx. So in small examples, it's often the case that Bx is the sum over y less than or equal to x of v to the length of x minus the length of y delta y. Okay, so for example, if you were to go away, so in principle, I've given you enough now to go away and calculate this. And in an S3, you would say this is always the case. And then in S4, you would discover like B of S2, S1, S3. S2 is delta S2, S1, S3, S2, plus a whole lot of boring stuff that satisfies this thing. So this would kind of, say if you if here's the identity, and here's S2, S1, S3, S2, this formula is saying the coefficient here is 1, and then you get V squared, V squared, V squared, V squared, V squared, as you come down Brouwer order. And then in this particular example, you would see like V plus V cubed times delta S2 plus V squared plus V4 delta identity. Okay, so everything would be boring except for these two kind of interesting dudes here. And this kind of amazing story, you know, from the 70s, where so people were also interested in the multiplicity of simple modules in highest weight modules. And if you work in infinite dimensional highest weight modules, and if you work out many of these examples, you just get some predictable multiplicity 1 based on Brouwer order. And Valence and Bernstein first discovered an example for SL4 that's very complicated to find, and they saw this multiplicity 2. Okay? And that multiplicity 2 is basically like exactly this coefficient. So I remember visiting Janssen in Aarhus, and he pulled out this old note of Valence and Bernstein, and then, you know, there's mass, and then there's this pointing out this 2, and Janssen has all these circles around it, an exclamation mark, exclamation mark, exclamation mark. Yeah? Okay, and then, you know, this is kind of crazy, but like there's theorems that say that essentially any polynomial with positive coefficients can occur here in symmetric groups. Okay? Like that's not exactly true. I can give the exact statement if you want, but basically these coefficients can be arbitrarily complicated if you go into very large symmetric groups. And then theorem of Kazan-Lustig for symmetric groups is that these H, Y, X are in positive coefficients. It's, you know, extremely unclear from the definition, and this is a theorem that Ben Elias and I generalized to all Coxeter groups several years ago. Yeah, so this is called positivity 1. Positivity 1 and positivity 2 is the fact that if you write the structure constants as some mu x, y, z, b, z, so these are some Laurent polynomials, then these mu x, y, z are in positive coefficients, which again is extremely non-trivial. So even so there's this paper at Foucault de Clou where he checks this for H4 and he needs to compute more than 1 billion of these polynomials. Okay, so now I want to advertise the following course. So now the idea is kind of funny. So in the classic algebraic treatments of canonical bases, what you do is you say, like, this is a whole bunch of algebra. And then you say, okay, you know, for some kind of deep reason, there's positive coefficients. Yeah. But now the idea is to kind of turn this around and then say that the KL basis so is to use positivity as part of the definition. It's the simplest basis satisfying P1, P2, and B delta.
So you exclude SD, the evolution.
Yes. So you exclude SD, but also note now that this doesn't use any V's. Like this, we can formulate this without, like there's a natural analog of this where we ignore the V. And so this philosophy also makes sense for the group algebra of the symmetric group, for example. You know, all I ask is that my basis should be, you know, upper triangular with respect to Brouwer order, and it should be positive. And kind of computational evidence that I find so, and simplest is kind of, this is very tricky. And I would say that we don't yet have the right notion of simplest. But I want to give you various pieces of evidence that this might be a good philosophy. But I would love if someone has some idea of what simplest may mean. So, are there any questions?
I have a silly question.
Sure.
Is it easy to generate order bases that satisfy these conditions but are not simple?
So you want one example of such a basis?
Yeah, which is a different one, and that's clearly not simple. Whatever simple means.
Yeah, so that is difficult. Even to provide any basis that satisfies B triangle, P1 and P2 is non-trivial.
Yeah.
But in general, we do know that there are many. So in high rank symmetric groups, we know that there's many, like that we have various reasons for knowing that there are many. And yeah, so one, in some sense, like, you know, when I discuss this Kashiwara-Saito example, this is an example of two bases which look extremely similar, will both satisfy this positivity, and are not the same. And then we would like to say that the Kajalitsik basis is the simplest for whatever reason. Yep.
So when you consider development algebra, it's quantum computer.
Yes.
So the canonical basis is replaced by the canonical one.
Yes.
And what's the replacement of the X?
So that is, so in classical enveloping algebra, you have PBW basis. When you quantize, there's now a choice of PBW basis, which relies on some choice of reduced expression for W0. And then essentially the canonical basis is the thing that works for all those choices. So you can just fix one choice and then that can be your delta x's. Always. Well, I mean, there's a way of normalizing it. So the canonical basis always is positive in PBW. And, you know, of course, there's like various versions of the canonical basis and some might have alternating signs and you have the same thing here. But there is a way of normalizing such that the canonical basis is positive in any choice of PBW basis. Yeah. And also, like in this story, you know, if you're interested in the canonical basis, there's another way of saying that where you yeah, I mean, there's some way where you can say Bx, By is asymptotically orthogonal, yeah, which is the asymptotically orthonormal, which is the analog of the quantum group that Lustig's carrying. Yeah.
There is one question from Zoom chat asking, what was the name for B delta property?
Brouwer upper triangular. Did that make it through the zeros and ones?
Brouwer upper triangular.
Yeah.
So if you
if you multiply B with delta, it is positively extended to delta.
Yes,
That's another.
that's another one.
So can you like give an additional condition like P3?
Absolutely. Yeah.
And,
There's P1, P2, P3, P4, P5.
oh, okay.
There's like an insane number of like amazing positivity in this basis. Yeah. And of course, you know, if you add P3, then the optimization problem becomes even harder to satisfy. But you know, at this stage, it seems like this is the weakest thing that has some. Yeah. And it's very fun, like if you like this kind of thing, to add various. You know, it's kind of like you can solve. So I'll explain in a second some framework in which you can solve this in certain cases. And then you can just add and subtract, like, you know, what about just P1? What about just P2? What about P2 and P3? What about P3 and P4? And somehow I find the answers like quite unexpected. You know, I don't have a good mental model that allows me to predict which optimization problems will yield this basis and which won't. Yeah.
Do you ever see a situation where some coefficients are not just positive Laurent polynomial, but they're sums of quantum integers?
So that is the case here, and that is something that I proved with Menelaus. And that was really hard to prove.
Is it by hard Lefschetz?
Hard enough chance, yeah. So, you know, that's like P9 on this long, you know, that's a stronger positivity property for these coefficients. But that's a property that needs V to be able to see it. So I'm kind of more keen on positivity properties that don't need V. Thank you for the questions. I appreciate it. So just example of, so here's a conjecture which I'm kind of annoyingly unable to prove, and it shouldn't be hard. So this conjecture, potentially someone that knows what they're talking about could just prove this easily. But I tried for several days and couldn't prove it. Bunch bases satisfying Brouhaha triangularity, P1 and P2. The KL basis. So let's say that we have such a basis called Bx prime, which we expand in Hyx prime delta y. So this is just some basis satisfying this amongst bases, so KL basis. So we would like some measure of simplicity over all bases, and we sum. So this is a positive Laurent polynomial. So we sum over all x, and we sum over all y, and we sum up the coefficients. Okay, so this is just a very silly measurement of how simple a basis is, namely, you know, what's its kind of total mass or something like that in the standard basis. So as I said, this is probably not a super difficult conjecture, but I would love to know it's true. Computational fact, which I kind of find so if you take Bx, this Cauchy-analytic basis, and you specialize V equals 1, we get this remarkable basis TSN. where n is less than or equal to 7, this AX minimizes some minimizes this same functional, except now, so now we're in the group algebra. So if this is not clear what I mean, then tell me and I'll make it more explicit, but such subject to kind of much weaker assumptions. So I want to write my so I write my basis with these a, y, x primes. So the coefficient should be positive. A for a simple reflection is just s plus 1. So this is often you have to assume something like this for the very simple generators. AX, AY is in so these guys have positive structure constants, and for AW0 is the sum of the natural idempotent corresponding to the full symmetric group.
D instead of 4. ABC 4.
Fair enough. D. Sorry about this. So the sum of coefficients is, of course, just the sum of A. Okay, so and there's, if you look at our paper, there's various kind of versions of this. Like some of them just require positivity for multiplication by this guy AS on the left and the right. And I already kind of find this amazing that this basis that's extremely non-trivial, for n equals 6, 7, this basis is very complicated. It has very large coefficients and things like that. But it emerges as the solution of a pretty reasonable looking optimization problem. And it's kind of interesting. So if you think about how to solve this, so you introduce variables like this. And then, this is a linear constraint. This is just some equality constraint. This is a gain inequality constraint, and this is a quadratic constraint. And so you need to use a quadratic solver. And this is quite hard to actually do for n equals 7, given our knowledge of optimization. But we can do it, and we get this optimum. And it's funny because n equals 8 is the kind of first interesting case, and it's also we just cannot do it. Like it's the first genuinely interesting case, and our optimization just doesn't, we're not good enough at these quadratic optimization problems to solve this on computer. Okay, but it'd be super interesting to know what happens.
So what is the sum of coefficients for x? I mean the exact value.
Oh, it's really hard. It's very complicated. Yeah, I mean, if I just give you an x, and I say how many elements are less than or equal to x in Bruja order, it's a very complicated question. And then you can say, oh, great, but there's this reweighting by kind of Kaczmarczyk coefficients, but it's still very, very complicated. Yeah. I mean, if you could find some value for this, I think it would be really lovely Like the value for this functional on the casualistic basis or the value for this on the casualistic basis, if that had a nice formula, that would be very nice, but I'm completely unaware of such a formula. So what's the time now?
You still have 37 minutes
Okay.
if you want.
I'm just about to discuss invariant cones, but would you like a short break?
If you want, you don't have to.
I mean, I can't concentrate for more than 45 minutes, so maybe 7-minute short break and then I continue.
Sure.
Okay. So now this is kind of fun. So if we take a partition of n, so this means lambda is a partition of n, we get d lambda simple, well, let's call it s lambda. What should I call it? I don't know. What should I call a simple representation with symmetric group? Q1?
Over CS lambda.
S lambda. It's
Or
over C.
finite
S lambda.
D lambda.
Okay. S lambda, irreducible module. Sn, and of course, all irreducible modules occur in this way. And then the KL basis leads to a, I won't explain how, but it's very standard, leads to a lambda such that the AX acts positive coefficients. And now the idea kind of is to look for bases of S lambda where AS equals 1 plus S all active. So this is for S as a simple transposition. Okay. So, the motivation for me for this question is we're stuck at n equals 8 for the big algebra. One can go much further if one concentrates on irreducible representations. And then maybe if we can answer this question for irreducible representations, then this will give some kind of partial information which we can then use to push our original question further. But this question turns out to be super interesting, I think. And bases such that the AS act positively. So if I have some basis, let's say CT, such that these act positively, then I get this cone, which is the direct sum this is a cone invariant under all AS. And one might hope that, one nice measure. So before I had this philosophy, okay, this basis is the simplest basis such that something is positive. Yeah? And so now you could hope is that simple is the same thing as maximal under inclusion. cones. Yeah, because if I have some basis, so imagine that I have some big cone that's maximal. This says that like if any other basis, let's just kind of fantasize for a second. So any other basis that's positive, like leads to some cone that's inside this cone. So that would say that that basis is expressibly positively in terms of my maximal one. So it would kind of say that my maximal one gives rise to all these other cones. Now, this is a completely so we have such a cone. We have at least one cone. But one thing that I was very amused by is, so maybe this shows that my intuition is not so good, but given operators A1, AN, in the endomorphisms of V, and this is a real vector space, bidimensional real vector space. It is undecidable a proper So I was kind of shocked by this. So proper means pointed. So I don't know whether you're also shocked by this, but okay. So I have some vector space, and I have some operators A1, A2 on the vector space, and then I look for a pointed cone. So this means that I want some cone like this, such that that plus its negative is the zero vector. So this means it doesn't contain any vector and it's negative. And so that means that's what pointed means. And now I look for cones that's stable under A1, A2, A3 up to AN. And that turns out to be undecidable whether such a cone exists.
What do you mean by undecidable?
I mean, in the normal sense of Turing machines, etc.
Really?
Yeah. So there's undecidable problems that can be encoded as the existence of an invariant code.
Any is a dimension or just any number?
Just any number.
Any number.
A finite number. Yep. And it's already false for 4 operators acting on a 4-dimensional real vector space. Completely bonkers to me. But anyway, that's life. But anyway, as I said, we're not in this case because we know that there does exist. The causality basis gives us such an invariant code. And then there's a theorem of, which I was kind of surprised that by Maestrik and Potosov, that. So I don't know who these authors are. If a proper invariant cone exists, then so does a maximal and minimal such. Okay. So theorem in this paper that I cited at the start, KL basis respectively dual KL basis agrees to maximal for lambda in 2 columns hook n minus 1, 1, n minus 2, 4, n that's equal to 8. Okay, so in many of the examples that you would first examine, this philosophy is nice, and the maximal cone corresponds to the Cauchy-Lewis basis. Again, not for all coefficients.
Really question. Isn't n minus 1 comma 1 is true?
Yes. Not silly question. Okay, so just an example to illustrate what's going on.
So you conjecture that this may be true for all lambda.
No.
No.
So, yeah, so what I'll explain in a second is that this maximal minimal is not the correct simple definition in general, but it's somehow it's approximation of the right definition because it's true in many cases. So, if we take the this is the rep to 1 3. So this is the action of S1. S1 acts by reflecting in this hyperplane. The action of S2. And now how does 1 plus S1 act? I take my vector and then I act and I add the two together. And so that's the same thing as projecting on this and multiplying by 2. So it's 2 times, so 1 plus S1 is equal to 2 times projection onto S1 fixed points. Similarly, 1 plus S2 is 2 times. Okay, and there's so now, so if let's say that our cone, for example, so one of the things that you can see in this theory is that the cone, such an invariant cone has to contain the eigenspace, the Frobenius-Perron eigenvector of any sum of these two operators. So if I take their sum, I get that my cone has to contain something like a vector like this. And then it has to contain the projection of this vector onto this fixed locus and the projection onto this fixed locus. So it has to be at least this cone. So this is the minimal cone, and this is exactly spanned by the fundamental weights. And then if you try to make this bigger, what you notice is that you can kind of extend this out, but you're not allowed to have anything that projects with a negative coefficient onto this axis. Yeah? Because otherwise then this cone would no longer be pointed, because I'd have something here and something over here. Yeah? And so it turns out that the maximal cone this guy. Okay. And which Lie theorist can recognize this maximal cone? Okay, so this is alpha and this is beta. So this is exactly the cone spanned by the positive roots. And so this is the kind of cone of positive weights, and this is the cone of positive roots, and they emerge in this framework in a natural way. So the cone of positive weights is the minimal cone, and the cone of positive positive roots is the maximal cone. Okay? And this, if you check through things, this is the KL basis. This is the dual KL basis. Yep. And of course, these irreducible representations always have an invariant form, and the minimal and the maximal are related by duality. Okay, and now something kind of interesting happens. So up to n is less than or equal to 8. Is there any questions based on this example? So this example holds for the natural representation of any file group. So these kind of cones emerge naturally. So 4 equals 9. KL basis equals maximal cone. Very cone. For lambda less than the partition 4 or 1. So this is the first thing where things go wrong. And here, not simplicial. So one thing that I should have pointed out earlier is that these invariant cones coming from bases are always simplicial cones. And so if you would like this this basis to emerge as a maximal or minimal cone, that minimal or maximal cone had better be simplicial. Okay? But you have some kind of picture like this, which is, I think, well known to people who are used to thinking about toric varieties. So this is what the minimal cone looks like. This is some there's the minimal cone. And then you have some basis, like something like this. This guy is the dual AL cone. But there's this other guy here. Funny business. Okay, so we don't see any way to kind of say a priori that this cone, this simplicial cone is better than this one. Okay. Yeah, and maybe just to re-emphasize, like, this is very much the place where this kind of subtleties with Kashiwara-Saito type stuff start showing up. And so maybe it's not unexpected that there's this kind of interesting phenomena that show up around this point. And yeah, I was going to comment on the kind of possibilities of reinforcement learning, but I think I'll stop there. And thank you very much.
Why not commenting on reinforcement learning? Yep, plenty of time. Just a few words? No?
Sure, yeah. Any questions? Like, is this roughly clear? Like, this is meant to be a two-dimensional picture of some phenomenon that's occurring in a very high-dimensional space. You know, I don't know exactly what the dimension of this representation is, but it's pretty high-dimensional. But you know, so this would be a cross-section. So you know, in toric varieties, you learn that any cone in 2D is simplicial, and then in 3D there's this first example of a non-simplicial cone, which gives you a non-rationally smooth toric variety. You know, of course, this happens much more frequently in high dimensions, and this is kind of what happens here.
What did you were having is
Funny business.
funny.
Yeah. So we don't understand what's going on here. There's some mysterious other basis which looks very nice from the point of view, like it's positive. You know, it's kind of indistinguishably good. So in some sense, so there's this philosophy that simple should have there should be some definition of simple. And we're trying to find the definition of simple. And this inclusion of cones business seems to work quite well for a while, but then breaks down. So we need some better definition of simple in order to say, like, this is the cone you should look at, not this funny one.
So maybe when you're talking about reinforcement learning, is it about finding better cones, or is it about better cones in these modules, or is it about finding bases in the whole?
Yeah, so I guess so. I'll briefly comment on the reinforcement learning possibility. So how do we actually compute? Like, how does one? So there's various extremely bad ways to compute canonical bases or the caracteristic basis, and there's essentially one good way. And this is the following. So you assume that the Bx is known for all x less than some target z. And then you choose z is smaller than z for some Okay, so you choose some S that makes Z smaller. So this is the kind of target. This is what we would like to compute. And now we know that there's at least one S such that we can multiply it on the right to decrease the length of Z. And then this guy is known. And then you form B ZS times B S. And then this is equal to BZS plus some typically very small number of kind of error terms. So this would be U. So there's some formula here. It doesn't really matter what this formula is.
The first term is not BZ. On the
Yes.
right hand side.
No.
Right hand side.
Yeah. Thank you. And now, and so, in this picture of the Bruja order, we have some Z. We assume that everything up here is known. We find some ZS just below it. We do some easy operation. We multiply up. And then the result will be, so we got this easy result. And then the tricky thing is we need to subtract off these terms. So if you can rewrite this as BZ is equal to this thing, this easy thing that's known by induction, minus some other stuff that's known by induction. So you go up and then you go, minus this, minus this, minus this, minus this. So that's the way that one computes the canonical basis element. But if you do this in practice, what you can see is that there's some kind of like So we have this operator where we move up and then we remove some small number of terms. And if we remove too much, you immediately kind of you immediately see that things go very bad. So the idea is to kind of potential RL algorithm. So we want to so the reward is some total sum of coefficients. And the allowed moves are given a partial basis by 1 via and then BZS times BX minus some terms, where these are already in the basis. Okay, so and it seems to me that it would just be very, very interesting and fun to give this to various reinforcement learning algorithms and see what happens. And I would strongly suspect that in in essentially any example we can compute, it would just spit out the KL basis. But that has not yet been checked.
But this algorithm somehow assumes your conjecture. Minimizing the total sum of the functions.
No, so the important point here is that the RL algorithm is not guaranteed to yield some global minimum. Some global minimum, by no means. Yeah, and in some sense, like I think that these formulations in terms of like the casualistic basis is the simplest in terms of it optimizes some functional. Like I suspect that's too simplistic, but I suspect that something like this may be true because there's some kind of prior of like, there's like some operational simplicity here in some sense. Like, you know, you just do these simple operations, you multiply, you subtract, you multiply, you subtract. And that the simplest basis that can be obtained in that way, you know, I hope will be the canonical basis. It's like, yeah, it really comes down to the question of like, what is the simplest basis? How do you define the simplest basis? And this is more, the RL algorithm would give you some minimum in a kind of operational sense, but not guaranteed global minimum by any means.
Are you trying to find a question whose answer is casualistic basis?
Yes.
Or, okay.
Yeah, exactly. Yeah. And ideally a version of this question that also works for the symmetric group, like without the V. Like this, I would say that, like I would be shocked. Like I feel like even you could just prove that there's some RL algorithm that would spit out the casualistic basis if you're allowed the V. If you're allowed the deformation parameter. But I'm particularly interested in this when you don't have the deformation parameter, because this would mean that there would be many other situations where you could have some way of just looking for a casualistic basis, for example, or looking for some canonical basis. Because there's many situations in which we suspect that there may be a canonical basis, but we don't have any kind of means of finding it. And this would provide a new means of finding it.